What if everything inside space, matter, fields, even you, could be fully described by information living on a distant surface? That's the holographic principle. Here's the fast deep dive. The seed of the idea came from black holes. In the 1970s, physicists found that black holes have entropy, information content, and it scales with the area of the event horizon, not the volume inside. That's weird. Most systems store more information as you add volume, but a black hole's information seems to live on its surface. Jacob Bekenstein and Stephen Hawking worked out the numbers. Entropy is proportional to horizon area, roughly 1 bit per tiny Planck-sized patch. The universe was hinting boundaries might count more than interiors. In the 1990s, Gerard Hooft and Leonard Susskind pushed the idea further. Maybe any region of space can be fully described by degrees of freedom on its boundary. Like a credit card hologram, a 2D film encoding a 3D image, reality might have a lower dimensional description that captures everything inside. The most concrete realization came in 1997 with Juan Maldacena's ADS-CFT duality. In plain language, a gravity theory in a particular curved space, anti-de Sitter space, is exactly equivalent to a quantum field theory without gravity living on that space's boundary. Two completely different descriptions, one identical physics. If that's right, information doesn't vanish in black holes because the boundary theory never loses track of it. The hologram keeps perfect records. So what does this buy us? Gravity is hard to reconcile with quantum mechanics. On the boundary, where there's no gravity, we can use ordinary quantum tools to answer questions that are brutal in the bulk. It's like solving a 3D puzzle by switching to a 2D instruction sheet that encodes the same content. Even more striking, in holographic models, entanglement, the quantum connectedness between parts, seems to build spacetime itself. There's a precise relation, the Ryu-Takayanagi formula, that ties the area of certain minimal surfaces in the bulk to the entanglement entropy of regions on the boundary. Translation: the geometry of space tracks, patterns of quantum entanglement. Where entanglement shrinks, geometry can pinch. Where it grows, geometry can stretch. Space-time looks less like a backdrop and more like an emergent pattern of information. What's actually been tested? We can't run a ruler along the edge of our universe, but in the ADS-CFT setting, thousands of cross-checks line up. Particle spectra, scattering, thermodynamics of black holes, signatures of quantum chaos. Holography has even become a practical tool outside gravity, modeling strongly interacting materials and quark-gluon plasmas that are otherwise painful to compute. Caveats matter. Our universe appears closer to de Sitter space, with positive acceleration, not anti-de Sitter. A clean, fully rigorous holographic dual for our cosmos is still an open problem, and we live on a wall is the wrong takeaway. The boundary isn't a literal screen, it's a mathematically equivalent description. Both pictures, the bulk with gravity and the boundary without, encode the same physics. Let's clear a couple misconceptions. Holographic doesn't mean fake, it means dual, two languages telling one story. And it doesn't prove the simulation hypothesis. Holography is about equivalence between physical theories, not a computer running those theories. Why should you care? Because the holographic principle points to space and gravity as emergent, not fundamental bricks, but patterns arising from deeper quantum information. That's as radical as learning temperature is just molecules moving. If space-time is built from entanglement, then questions about the beginning of the universe, the fate of information, and quantum gravity itself become questions about how information organizes and protects itself. Where is this heading? 3 frontiers stand out. First, toward our universe, extending holography from ADS to de Sitter to match cosmic acceleration. Second, quantum error correction. The mathematics of robust holographic duals mirrors the math of error-correcting codes, hinting that space-time behaves like a code that protects bulk information from boundary noise. Third, complexity and geometry. Proposals like complexity equals volume or complexity equals action tie the difficulty of building a quantum state to geometric quantities in the bulk, linking computation to space-time shape. Bottom line, the holographic principle is a working bridge between gravity and quantum theory. It reframes reality as information arranged in 2 interchangeable ways, one with space-time, one without, and suggests that what we experience as 3D space could be the shadow of deeper quantum patterns. If that excites you, tell me what to tackle next. Black hole entropy in numbers, how entanglement stitches space, or whether holography can illuminate our accelerating universe.